they allows so-called isomonodromic representation. So in some sense, we may say that these equations are integrable, but in a sense, not in classical sense, because they are non-autonomous Hamiltonian systems. It turns out that these systems may be written in physical form, and occasionally these non-autonomous Hamiltonians are two-particle Inozemtsev systems. I guess Manin he wasn't the first who did discover it, because it looks like Painlevé knew about it itself, but I would like to say that Manin was the first who wrote this Inozemtsev form of the Painlevé-6 equation, and he wrote the elliptic form of the Painlevé-6 equation. But then Levin and Alshanetsky did realize that this form of the Painlevé equation is nothing but two-particle Inozemtsev system, but slightly deformed in the sense that the Inozemtsev systems, we may think about them as some generalization of the Calogero-Moser Hamiltonians, but deformed in the sense that they did the autonomization of the system and obtained that all Painlevé equations can be written as some Inozemtsev system with some deformation. And that's what we call Painlevé-Calogero correspondence. The natural question arises here about the n-particle Inozemtsev systems, because this is quite an obvious generalization of this system. And what is on the other side of the Painlevé-Calogero correspondence? What are these non-autonomous Painlevé systems? And partially this question was answered by Takasaki in his work, who did kind of derive the autonomization of n-particle Inozemtsev system and presented Painlevé-Calogero systems. The only question he didn't answer is the Painlevé property in the sense of these systems, or more important, he didn't tell anything about the existence of the isomonodromic problem for this multi-particle non-autonomous Painlevé-Calogero systems. And this question was answered 2 years ago by Bertola, Cafassa, and my collaborator Vladimir Rubtsov. And they described this equation, this multi-particle systems, as the Hamiltonian reduction of some non-commutative Painlevé equation, of some matrix Painlevé equations. And they did introduce the isomonodromic problems for all Painlevé-Calogero systems. Well, the approach of the Hamiltonian reduction usually says that there is some duality, because duality arises quite naturally in such approach. So this is the aim of my talk today, to show how this Hamiltonian reduction for the matrix Painlevé equation leads to some dual systems. And this is kind of plan of my talk. So first of all, I will explain what is the Hamiltonian reduction and Rusinar's duality. So here I will mostly talk about the Calogero-Moser system. Then I will try to give a brief introduction to Painlevé equations as isomonodromic systems, and what is Painlevé-Calogero correspondence, to show you some Hamiltonians and some exact form of this Painlevé systems. After that, I will briefly describe how to obtain matrix generalization of the Painlevé systems. And finally, I will show you their reductions, these Painlevé-Calogero systems, and the dual one, the Painlevé, which we call Painlevé-Ruijsenaars systems. And generally, I will try to describe how we understand this duality in terms of the spectral curve. So we call this duality spectral duality. So I will start from the Calogero-Moser system. So generally, I will talk about the following Hamiltonian systems with the following Hamiltonian. So we have a kinetic term and the interaction between the particles. This is not neighborhood-wise interaction, means that we have interaction of all particles with all particles, not only with the neighbor. So it's quite well known that when we take the potential in one of the following forms, so we have a rational potential, hyperbolic trigonometric, or elliptic potential. So this is Weierstrass P function. This system is integrable, which means that we can write down the n independent first integrals, and generally I would like to say that this system may be written in a lax form. So we have L operator, which has the following dynamics. Well, this is not a kind of a surprise, and now I just want to show you how to obtain the rational such a system called rational trigonometric or elliptic Calogero-Moser systems with such potentials. And now I want to show you how to obtain a rational Calogero-Moser system as the reduction from some trivial dynamic on the space with large symmetry. So that's what is the Hamiltonian reduction. And the main examples will be cotangent bundle to some Lie algebra, generally to GLNC, and to some Lie group. So we start from some symplectic manifold with the G action, with the action of some Lie group via symplectomorphisms on this space. And this action induces the map from the Lie algebra correspondent Lie group to the vector fields on our manifold. So it's given by the following formula. This is quite standard thing. And since we are working with the symplectic manifold, we can insert our vector fields to the symplectic form and obtain the one form. We call the action, we say that action is Hamiltonian action if for each element of the Lie algebra, the one form which can be obtained by insertion of the vector field to symplectic form is exact. So it means that all the vector fields that we get from this map are Hamiltonian. And then in this situation, we obtain that this map from the Lie algebra to vector fields may be expanded, may be transformed to the map from the Lie algebra to the functions on our manifold. Generally, we are more interested here not in this map, which sends an element of Lie algebra to its Hamiltonian. We are more interested in dual one, which we called moment map, which sends, so this is just a dual map. So we can think about the manifold itself as the subspace of the dual space of the functions. And the pairing is given by just the evaluation of a function at a point. And we have the moment map sends each point of our manifold to some element in Lie coalgebra. And here is the condition how to find this moment map. And generally, why do we care? We care because when we have such a group action, we can do a reduction of our phase space. So the theorem, the main theorem says that if our moment map is equivariant, which means that the following diagram is commutative. So how to think about this diagram? This diagram says that the moment map is a map from the manifold to Lie coalgebra, and this diagram says that the group action on the manifold lifts up by the moment map to the coadjoint action on the Lie coalgebra. So the theorem says that if moment map is an equivariant, then for any G invariant function, so it doesn't change under the G action, will commute with the moment map. So this kind of consequence from this theorem that if we will take G invariant Hamiltonian on some symplectic space, symplectic manifold with the G action, Hamiltonian G action, this will lead to the fact that the moment map will be a first integral of our system. So in some sense, we may think about it as the formulation of the Noether theorem in the case of the symplectic manifolds with the Lie group action. So to give you an example, we will start from the manifold with the cotangent bundle to the GLN. So I will just say that we may think about this manifold as the direct product of GLN with GLN because we have an identification of the GLN star with GLN by the Killing form. And generally, you may think about it as the space of two matrices, n times n matrices. Also, they also can be degenerate. So since it's cotangent bundle, we have the natural symplectic form, which is given by differential Liouville form on this space, and the symplectic form is given by the following two form on the space of this matrices P and Q. So generally, we may think about the following Poisson bracket, which quite easily. I mean, we may think just about this Poisson bracket on this space. And the action of the group will be just a conjugation, both P and Q by some element of the group. So this is, since, so it's easy to check that this action is symplectic. Moreover, it's not very hard to check that this action is Hamiltonian, in the sense that the vector fields are given by the following formula. And for each such vector field, we can write the Hamiltonian, which will be just a trace of psi with the commutator of P and Q. So what did we obtain? We obtained that the moment map for T star to GLN is given by just a commutator of P and Q. And what is a rational Calogero-Moser system in this picture? So we need to consider the free particle, in some sense, free particle in the space, and do a reduction. So let's maybe do it slowly. So we have the following Hamiltonian. It's easy to see that this Hamiltonian is invariant under the GLN action. So when we conjugate trace, it stays the same. So we have the following equations of motion, and as we mentioned previously, we have the following moment map, just a commutator of P and Q. Moreover, we can forget about all the stuff about the symplectic group action and Hamiltonian group actions, and just check that the commutator of P and Q is a constant of motion. So it's quite easy from the equations of motion. What is Hamiltonian reduction? Hamiltonian reduction is a procedure which were written by Kazhdan, Kostin, and Sternberg, and this procedure may be formulated in the following way. So first of all, we fix a moment map to be a very special matrix. This is identity matrix minus some rank 1 matrix. So you see that we have a tensor product of the vector with identities at each coordinate to itself, and we have some coupling constant. The main thing about such a choice, about this choice of the moment map, is that there exist the transition matrices to the eigenbasis of the Q matrix, such that they leave this value of a moment map the same. So generally, what we do, we take the moment map condition, then we conjugate it by this matrix C. So what we do, we diagonalize Q here, and we obtain the following commutator here. So X is diagonal matrix. So this is matrix of with eigenvalues of Q on diagonal, and Y is some matrix which was obtained by just conjugation of P by C minus 1C. And since since C is leaves our moment maps the same, so C is just a stabilizer of the following matrix, of the rank 1 matrix, V tensor V transposed. We have the same equation, but now for diagonalized Q, and we can solve it and obtain that Y is given by the following matrix. So you see here we have the commutator with diagonal matrix, so we cannot define the diagonal entries of Y, so we will have something here, but the off-diagonal entries are given by the following formula. And if you're familiar with the Calogero-Moser systems, you will say that this is well-known object. Generally, this is a lax matrix for the rational Calogero-Moser system. But what we do next? We see our Hamiltonian was just a trace of p squared divided by 2. And this object is invariant, so we may just put here p as the y conjugated by c, c minus 1, c minus 1, and we will obtain that the Hamiltonian writes as trace of y squared divided by 2, and we obtain that the Hamiltonian in these coordinates writes as the following dynamical system, the following Hamiltonian system. So we did obtain Calogero-Moser system as the reduction with respect to the following value of the moment map of the free particle system on T star to GLM. So if you will, I did choose the following names for the coordinates P and Q because they becomes Darboux coordinates. So after doing these gauges, our symplectic form will transform to the following one plus, which will give us the Darboux coordinates, plus we will obtain some additional two form, which we do not care about because our Hamiltonian doesn't depend on any entries of C. But generally, this part of symplectic form corresponds to constant Kirillov-Suryaud symplectic form on the coadjuvant orbit of the group action. Okay, so we did obtain Darboux coordinates here, and moreover, we obtain the lax equations because the equation of motion p dot equals to 0 will transform to the following one. So generally we will obtain that. Generally, we obtain that the first integrals are the eigenvalues of Y matrix, and this is in correspondence that Y matrix looks like a lax matrix for the Calogero-Moser systems, and that's how it works. So this is just this was a reduction by hands, and generally, what have we done? So we did consider equivariant moment map, and equivariant moment map means that we send an orbit of the action on the symplectic manifold to the coadjuvant orbit of the group action. So when we are talking about the reduction, we say that we take the the pre-image of the value of a moment map, and then we factorize by the stabilizer of the value of a moment map. When we did choose our moment map to be the following matrix, we actually choose the maximal element in the Lie algebra, which means that it has its non-trivial element with the biggest stabilizer. So if you will just try to see what are the eigenvalues of this matrix, you will see that it has one eigenvalue of the multiplicity 1 and one eigenvalue of the multiplicity n-1. So it has a very big stabilizer, which gives us that the reduced space, usually we have that reduced space has the following dimension. It's 2n plus dimension of the coadjuvant orbit. But generally, in this situation, we obtain that we do not have this additional dimension. So we obtain integrable system, but generally we will obtain the degenerate integrable system. So, well, to say a few more words about it, you may think about it as the extension of our phase space by the coadjuvant orbit. So we consider M cross, and the moment map is in this coadjuvant orbit, and then we do a Marsden-Weinstein reduction by the group action induced on this direct product. Okay. So
may I ask something?
Yeah, sure.
What do you mean by factorization? Is it smooth or algebraic or topological? Do you consider the algebra of invariant functions, or you do some smooth factorization by the group action?
Okay, let me think for a while. I think it's smooth factorization by the group action. The problem is that sometimes we will obtain not the manifold because we can obtain orbifold because we will have some singularities here. But yes, here I mean the smooth factorization by the group action.
Okay, thank you.
Okay, so the space I did consider called Calogero-Moser space. So the space of the matrices which commute as this identity minus rank 1 matrix. And the thing is that this situation may be illustrated by in the following way. So we have our, so this is kind of a sketch of the situation we do have. We have our manifold and we have the level set of the moment map, this blue line here. So we start from some point at this set, and then we are looking for the orbit of the group action. So what does it mean that we are again, that the diagonalization of Q matrix leads to the same moment map? It means that this orbit intersects this level set again at the point where Q is diagonal. So we start from some P and Q coordinates, and then we've got to the coordinates where X is diagonal. Generally, we may do the same for the P matrix, and instead of diagonalizing Q, we may try to diagonalize P. And this is another set of the coordinates. The procedure will be generally the same. We still have the big stabilizer of this element, so we will obtain the same situation. And if we will diagonalize P, so we will transfer to the eigenbasis of P, so we will obtain some matrix lambda, which is diagonal, and phi, which is non-diagonal, and it will be just a Lax matrix for the again for the rational Calogero-Moser system, but written in different coordinates. We will obtain that our Hamiltonian will become just a free particle Hamiltonian. So in some sense, we may say that another point corresponds to the action angle variables for the Calogero-Moser systems, for the rational Calogero-Moser. And the map between these two coordinates is just an action angle map. So and here we obtain this kind of duality. So if we will consider two different Hamiltonians, so before we did consider trace p squared divided by 2, but now we may consider kind of another Hamiltonian which is connected with the first one via some Fourier transformation. We will obtain that the first set of coordinates will send my first system to the Calogero-Moser system, but the second system will be written in the action angle variables, so it will be just a free particle. But the second set of coordinates will give me that the first system is written as the free particle system, while the second one will take the Calogero-Moser form. So this, what we call Rusinar's duality. So this says that, so generally Rusinar's duality may be formulated in the form that we have two different flows on the same manifold, and which are connected by this kind of Fourier transformation. And the two systems are dual when the action angle variables have the same. So two systems are dual when we have the situation when the action angle variables of one systems are the momentum and coordinate for the second system. So you see here I is the action coordinate, while here this is just a coordinate of the particle, and vice versa. Here I have q is the coordinate of the particle, while here I have that q is an action variable. So the same goes not only for rational Calogero-Moser system. We may consider trigonometric Calogero-Moser, and the dual will be rational Rusinar system. To do that, instead of considering cotangent bundle to Lie algebra, we consider cotangent bundle to Lie group. Well, doing the same, the symplectic form is given by the following differential of the Liouville form. So just to say a few words, this is a logarithmic form, and the moment map takes the following form. So here we consider two set of different. Here we consider two different Hamiltonians. Both of them may be viewed as the free particle Hamiltonians. First one is the same actually. The second one is a little bit weird, but instead of this one, we may consider trace p squared, for example. And the thing is that doing reduction at x, y coordinates, we will obtain trigonometric Calogero-Moser systems, while here we will obtain some kind of action variables. And at another set of coordinates, at the dual coordinates, we will obtain the first system is written in action angle coordinates, while the second one will take the following form, which is rational Rusinar system. So few more words about this situation. You see that before, when we did consider the cotangent bundle to Lie algebra, we did obtain the rational system, because in some sense the symplectic form we did consider was already written in the Darboux coordinates here. And when we did consider cotangent bundle to Lie group, we did obtain the trigonometric system because of this logarithmic behavior of symplectic form. So in some sense, I would rather say that the interaction potential is the property is the property of the symplectic manifold we consider, neither the property of the Hamiltonians we consider. So to sum up the things I did say about the Hamiltonian reduction, I just want to say the following summary: that systems which are written on the T star to Lie algebra or T star to Lie group may be reduced to the multi-particle systems in Calogero coordinates or in Rusinar's coordinates. So we may consider any other Hamiltonians, not only free particle Hamiltonians. We may consider any polynomial, any Hamiltonians of the form trace of polynomial in Q, P, Q minus 1, P minus 1, and obtain some reduced systems which will be written in some multi-particle form. Okay, now I will shift a little bit to Painlevé equation. So this is the second topic of my talk. So first of all, I will say a few words about the Painlevé equations. So the Painlevé equations are equations which are which have Painlevé property. This Painlevé property may be formulated in the following form. So we consider differential equation, and the solution of the differential equation has Painlevé property when the critical singular points do not depend on the initial data. So there are few very simple examples. So the first example is the following first order equation, and the solution will be that we have exponent of z minus z0. So we see that the solution has only one critical point at infinity, and this critical point doesn't depend on the initial data, on z0. So critical points are the critical points it's root type singularities or logarithmic singularities or essential singularities. So here we have one essential singularity at infinity which do not depend on the initial data. The second example is also has Painlevé property because the solution may be written as 1 divided by z minus z0. So we see that the singularity depends on the initial data. We have the pole which moves z0, but this singularity is good in some sense. So it's not a root type singularity or logarithmic singularity. So we say that the solution also has Painlevé property. And the third example, which says that the solution is 1 divided by square root of z minus z0, not equals, but functionally equals. And we see that in this example, the root type singularity depends on the initial data. So we do not have Painlevé property here. So in case of first order equation, the classification of the equations which has Painlevé property quite simple. We have the classical functions, we have rational functions, elliptic and entire functions. But when we try to classify the second order equations, we obtain some 6 new functions which are called Painlevé Transcendence, and they are not elliptic or rational, entire, and so on. But they are also have Painlevé property. So maybe the more important thing about the Painlevé equations that they are maybe obtained as the isomonodromic condition for some linear systems on the Riemann sphere. So what do we do? So here I will talk only about, not about all Painlevé equations, but generally I will talk about the Painlevé-6 equation. So we consider the following linear system on the sphere with 4 punctures. So we have punctures at 0, 1, t at infinity. Just to say, we may also write down this system in this way because we may fix 3 points by the Möbius transformation. So we consider the following system in the sense that psi is element of some Lie group, and AIs are the element of the correspondent Lie algebra. So fundamental solutions. Fundamental solution of this system has monodromy, which means that when we started from some point at our Riemann surface and we fix the solution there, so we may think about the initial value. And then we prolongate the solution around the loop, around each singularity. We have the fundamental solution changes by the multiplication of some matrix, which we call monodromy matrix. And the natural question is the following: how should AIs depends on the only parameter in our system, on the T, such that the monodromy matrices do not depend on this parameter? And the answer to these questions are so-called Schlesinger equations. You may see them here, and they are equivalent to the compatibility condition of the following linear system. So what we can see here, we can see that these Schlesinger equations are written in a lax form, in the sense that each derivative of AI may be written as AI with something. So it means that the eigenvalues of AIs are constant. And moreover, we can see that the sum of A's are constant of motion. And this means that the residue at infinity is a constant of motion for our system. So why do we care about the Schlesinger equations? Because when we consider SL2 situation, Schlesinger equations reduced to the Painlevé-6 equation. So in some sense, Painlevé-6 equation parameterize such Fuchsian systems, which has monodromy, which do not depend on the deformation parameter. So generally, the things about this Painlevé equation may be reformulated in the language of flat connections. So generally, we consider fork-hole sphere, and we consider holomorphic connection of G bundle here with only simple poles at these punctures. And this deformation parameter T, since we want that the connection, since we want only simple poles for the connection, the deformation parameter T lives on the three-hole sphere, and the isomonodromic deformations are just a flatness condition for the following connection on the SL2 bundle or any G bundle on the following space. And it turns out, and in this picture, it's we can see naturally that the isomonodromic deformations are Hamiltonian. Hamiltonians are given by the following residues: the residue of trace A square at point T, and the symplectic form is given by the Atiyah-Bott symplectic form on the space of connections, which is in fact equivalent to the following phase space. So we put our residues at each singularity to the coadjoint orbit, with constant Kirillov-Suryo bracket, and here we have additionally gauge group action, and for the right hand side we have the diagonal adjoint action, and this condition that the sum of residues is equal to 0 is just a moment map of the gauge group action. So again, in some sense, we are talking about the Painlevé-6 equation as the SL2, as the parameterization of the SL2 flat connect holomorphic connections on the four-punctured sphere. Now I did mention that these isomonodromic deformations are Hamiltonian, and that means that we can write the Hamiltonians for the Painlevé equations. And it was made by Okamoto, and he showed that for all Painlevé equations, not only for P6, but for the whole for the whole set of the Painlevé equations, the Hamiltonians are written as some polynomial functions in Q, P, Q minus 1, and T with the following symplectic form. So since our Hamiltonians are not autonomous anymore, we have to consider the extended phase space. The theorem by Manin, which is generally Painlevé-Calogero correspondence for P6, says that there exists some symplectic map from the set of these coordinates. So this is kind of Okamoto coordinates to some other coordinates, which I will call elliptic coordinates. So since it's symplectomorphism, it sends the following symplectic form to the following one, and this H elliptic may be written in the following form. So in some sense, this Hamiltonian rather better than this one. I didn't show you this one, but it's quite big, and it's just a polynomial which contains the multiplication of Q by P, so it's not physical. But this one is written in the natural form, so we have the kinetic part and we have the potential. And the thing is that the time here, our parameter, is the modular modulus of the elliptic curve. So in some sense, what Manin did, he wrote Painlevé-6 equation as the function on the moduli space of the elliptic curves. So and occasionally this form, this was mentioned, as I said before, by Levin and Olshanetsky, that elliptic form of P6 is a deformation of two-particle Inozemtsev systems. And this works for all Painlevé equations. And this result may be obtained by a confluence for the Painlevé equations. And you may know this procedure as Inozemtsev limit. But here we have to deal with non-autonomous version. Yeah, so this gives us the Painlevé-Calogero correspondence for the second order Painlevé equations, how to get to the n particle generalization. So the answer to this question is given by the consideration of the matrix Painlevé equations. First of all, I should just say what it is. So generally, we consider the SL to n bundle over four-fold sphere with simple poles. The phase space is so generally we consider generally this phase space is equivalent to the direct product of three coadjuvant orbits, and the reduced phase space with respect to the gauge group action is the following one. So here we have generally here we have quite standard procedures that we put our moment map A infinity to some coadjuvant orbit, and we consider the extended phase space and do the Marsden-Weinstein reduction with respect to the gauge group action. So briefly, we consider the well-known relation which says that the sum of the residues equals to 0, and we solve this equation to obtain the reduced phase space. So the dimension of the reduced phase space will be just, we need to calculate it, and it will be just 3 dimensions of the coadjuvant orbits we did choose at each point. minus dimension of the SL2n group, because we did reduce with this moment map condition, and also we have to minus the stabilizer of A infinity. So it may be viewed as the additional action of the Cartan torus on the reduced phase space, which we forget when we do just resolution of this equation, that we can actually act by the Cartan torus again. So when you consider A infinity to be conjugated to some diagonal matrix, this will be exactly the dimension of Cartan torus of SL2. So this is a general system on the SL2 bundle over the four-fold sphere, but the Kawakami mentioned that if we will consider the following situation when we have not fully when we have lower dimensional orbits, and this may be written in the following way, that these AIs, these residues at the finite points, may be written as a tensor product of the SL2 cross GLN, and we choose the following value of the A infinity. Schlesinger equations for such system will be equivalent to the matrix version of the Painlevé-6. So this matrix version of the Painlevé-6 is quite simple thing. We just take the Akamoto rational Hamiltonian, put the matrices in this Hamiltonian, and then we take a trace of this Hamiltonian. So it's kind of quite obvious generalization of this Hamiltonian. And the dimension of the space will be the following. So when we consider the orbits which are given by the tensor product of GLN with SL2, the dimension of the orbit will be 2 multiplied by n squared. So the dimension of SL2 is 4n squared minus 1, and the dimension of the stabilizer of this A infinity is just n squared and plus n minus 1 squared. So we obtain that the dimension is 6n squared minus 6n squared plus 2n. So the dimension of the reduced space is 2n, which says...
Yeah, I'm sorry. I missed something very important. Could you repeat the previous page? AI, so the residues of a connection, they are element of SL2n, isn't it?
Yes, yes.
Theta I are just numbers.
Yes, this is eigenvalues actually. So yeah, it means yeah, maybe it's better to say. Oh, I can hear someone. Okay, so generally
it is important that they are not simply in SL2 times n, but they are two n blocks of two times two matrices.
Yeah. So generally, Kawakami motivated this by the considering by the consideration of the matrices with the eigenvalues of multiplicity 2, because generally for the SL2n matrix you have 2n eigenvalues which are connected by the trace equals to 0 relation, but here you have n different but here the situation is a little bit more specific. I mean, the multiplicity is not 2, but you have that the set of the eigenvalues looks by the following way. You have the eigenvalue and minus this eigenvalue and so on. Okay.
Thank you very much.
Yeah. Okay. So in other words, we can say that in some special case of degenerated orbits, the isomonodromic problem of this flat holomorphic connection may be parameterized by some P's and Q's, or by some smaller dimension objects. And the thing I didn't mention, that this matrix Painlevé equation is written on T star to GLN. So this is not just a Hamiltonian. We have the right symplectic structure, and moreover, this Hamiltonian is polynomial in this variables. So it's automatically invariant under the action on the under the GLN action on this.
Ilya, could you show the formula for the Hamiltonian?
Yeah, sure. This is the next slide. So I didn't put here formula for P6 because it's quite big and may cause an anxiety, but for other Painlevé equation, you can see the formulas here. So you see all of them are, generally all of them are polynomials in P and Q, except of one Hamiltonian, which is here. And for all of them, we have that the commutator of P and Q is constant. So generally it's the same as they are written on T star to GLN. And now I will give you an example of Painlevé-Calogero 1. So this is probably the simplest case. So we consider the following Hamiltonian written on T star to GLN. So in Calogero coordinates, we will obtain that the reduced Hamiltonian takes the following form. So we see that the diagonal part is still the same uncoupled Painlevé Hamiltonians, but we have also coupling part of the Hamiltonian, which looks like the Calogero-Moser 1, the rational Calogero-Moser 1. That's why we call it Painlevé-Calogero. And on the other hand, we can try to reduce at the dual coordinates at this lambda and pi when we diagonalize not q but p, and we obtain the following the following Hamiltonian system. So it looks not the same as the previous one. You see that we again have the rational interaction potential, but here you have that this is moments are in the lower part of your ratio. So in some sense, if you will quantize this Hamiltonian, you will obtain some differential operator. But if you will quantize this Hamiltonian, you will probably obtain some difference operator because of this part. But it depends how you will quantize it, of course. Okay, so this is just an example. We have the same examples for the Painlevé-2, Calogero, Painlevé-2, and other. So the main question, how to get an isomonodromic problem for the reduced system, and this question was answered by Bertolakov-Asartsov. So the answer is to lift up the reduction on the space of connections via gauge transformation. Dima, do you have a question?
Yes, I have a question. Maybe it's better to state it at the end, but I have an impression that the multi-variable generalization is always a quantization, is a sort of quantization. Am I right? Because you changed your commutative variables by matrices, there is some sort of quantization.
In some sense, but I would like to say that, we may think about this as the quantization of the Painlevé equations, but I think it's better to think about it as a consideration of higher rank flat connections. so higher rank G bundles. So it's in this picture, it's not like a quantization, it's like a generalization.
Okay.
So,
Mm-hmm.
but yeah, you're right. Yeah. Okay. So yeah. So how to get from here to the isomonodromic problems for this matrix for this multi-particle Painlevé equation? So as I said before, matrix Painlevé equation means that our connection takes values in some tensor product of SL2 with GLN. So we have that, for example, we have our linear system of the following form, and the A and B matrix may be written as the block matrix here, where these blocks are polynomials in P, Q, and Q minus 1. So in some sense, A lives in SL2 across our T star to GLN, maybe C infinity to T star to GLN. And when we did reduction procedure, we did the conjugation by some matrix C of Q and P. And now we consider very special gauge here. So we take the transition matrix to the eigenbasis of Q and consider the following gauge transformation. Then we will have that actually our A matrix will be just conjugated by this G, but since A is written as, okay, our phase space M, I will call it like that, and SL2, and our gauge has a very specific form, we will obtain that our gauge will act by the conjugation on the phase space in some sense, and we'll leave SL2 the same. So generally, we will obtain that this conjugation will just change Q's and P's in L matrix by X and Y's, which are now written in multi-particle coordinates. And also the same goes with B matrix, but we will have some affine part, but generally we can find it using equations of motion. So doing this gauge, we obtain another linear problem of the following form, but which is written in the multi-particle coordinates. And obviously, it will give us the multi-particle equations which are given by the reduction from the Hamiltonian, from the matrix Hamiltonian we did consider before. And the same may, and we can do the same for the dual coordinates, of course, because generally the difference between multi-particle or Calogero coordinates and dual coordinates is just different gauges, different action of the groups. So this duality means that we have different gauge transformation for our isomonodromic problem. Moreover, this gauge transformation do not depend on the spectral parameter, on the point on the coordinate on the base of our isomonodromic problem, which means that generally we have that the initial spectral curve is the same as the reduced one here, because we can conjugate under the determinant by this gauge, and the same as the dual one. So we obtain a very, how to say, fancy property of these systems that they have the same spectral curve. And generally, it means that both dual system and multi-particle systems, so Painlevé-Calogero and Painlevé-Ruijsenaars systems, they are symplectomorphic in some sense. Anyway, I can write the formulas which connect the action, the action of one system with the action of the second system. Of course, now we are talking about the non-autonomous situation, so it's rather to say not action coordinates, but some Poisson commutative family here, but whatever. So, So, well, that's why we call this duality spectral duality, and well, it's also maybe viewed as the action duality. So now I will just show you the list of the Painlevé-Calogero Hamiltonians. So you should, and generally, these systems are obtained by reduction of the matrix Painlevé equation plus some symplectomorphism. Why do I say that? Because generally all the Painlevé equations, all the matrix Painlevé equations are written on T star to Lie algebra. But as I said before, the form of the potential is the property is a property of the phase space, not of the Hamiltonian system. And occasionally we did the reduction from the T star to JLM and obtained some elliptic systems and some trigonometric or hyperbolic systems. So that means that and that's why we need some additional symplectomorphism, which sends our rational systems to this elliptic ones. So we have that Painlevé-6 corresponds to elliptic Inozemtsev system, Painlevé-5 and Painlevé-3 corresponds to trigonometric or hyperbolic systems, while the Painlevé-4, Painlevé-2, and Painlevé-1 are the rational systems. So here, the main question is the following: how to get the Rusinar's systems from this scheme? And the answer is to embed T star to GLN in T star to in T star to Lie group GLN into T star to Lie algebra GLN via symplectomorphism. So to do this, I will just consider the example, and this is matrix Painlevé-3 equation of type D8. So the Hamiltonian, I already mentioned that this is the only case when our Hamiltonian depends on Q minus 1, which means that Q should be invertible matrix. So it's written not on the whole T star to GLN, but it's written on some open affine set in this symplectic space. And the lemma, I think this lemma may be well known. Occasionally I saw it in Nekrasov paper on duality, but he did it for a special case of unitary. So I think he did consider SUN algebra and SUN group, but whatever. The lemma is the following. So this opens affine set in T star to GLM to the algebra is symplectomorphic to the T star to GLN, where GLN is a group now. So the proof is extremely easy. So we just give an explicit form of this symplectomorphism. Of course, there are a lot of symplectomorphism, but this is one of them. And we just put it into Liouville form and obtained that the Liouville form we did consider for the T star to the algebra transformed to the Liouville form on the T star to Lie group. And returning to our Hamiltonian, we did the following symplectic transformation, which is a little bit, which is shifted by some constant. So it's still symplectomorphism. This is still symplectomorphism, and we obtained that our system, which were written on T star to GLN, rewrites as the following natural, in some sense, system on the T star to Lie group. And this how we can obtain, for example, trigonometric Painlevé-Calogero systems doing only reduction. So before, in the paper of Virtuola, Kafas, and Rubtsov, they firstly did the reduction, and then they did the symplectic transformation, canonical transformation to the systems. But now we do firstly this canonical transformation, which send our system to the natural form, and then we do the reduction and obtain the right form of this system. And again, doing some additional change of variables. So this is non-autonomous now, change of variables, but it's still symplectomorphic in a sense that it will shift our Hamiltonian a little bit. We obtain the following form for the Hamiltonian we did consider at the first time. So why did I care? Because now it's easily see that we have this system written on T star to GLN, which combines the free particle, which leads to trigonometric Calogero system, plus it combines the Rusinar's part of the Hamiltonian. So in some sense, Painlevé-3 equation gives us some combination of the trigonometric Calogero system and the Rusinar system, and reducing from different at the different points of the orbit, we obtain trigonometric Painlevé-Calogero system, and on the other hand, we obtain some Rusinar system with some shifts by this diagonal part. So, well, probably I want to tell a few things before I will finish my talk. So, what should I say more? All these systems may be all the systems which I did consider may be written as an autonomous system, so we can just freeze time and obtain some integrable autonomous system. Well, for some equation, it was well known because this Painlevé-6, Painlevé-5, and Painlevé-4 are just the autonomous versions of the Inozemtsev systems, so they are probably integrable and so on. But these three systems are kind of new ones. So, moreover, the open problem is how, I did show you how to obtain the trigonometric systems by embedding this T star to Lie group to the T star to Lie algebra, but the question is how to obtain elliptic systems, or in a sense, how to embed the phase space, which gives us elliptic systems as the reduced ones into T star to GLN. Well, and generally the question about the integrability of these systems, which correspond to the P3, P2, and P1. So are they integrable? Is there R matrix, for example? We still don't know, but I guess the answer is yes, because all the systems are obtained by the Hamiltonian reduction from the R matrix systems. So, and here we can just try to use the theorem by Zotov, Braden, and Morozov-Maronov, who did give and kind of receive how to obtain the R matrix for the reduced system if we did start from the R matrix system as an unreduced one. So I guess now I can finish and answer you to your questions. Thank you for your time. Hope you found it interesting.
Thank you very much. Ilya, I have some very simple question. I didn't understood the nature of this, of the multi particle generalization, the principle, the time variable is the position of the point. Am I right?
Yes, yes.
If the system is integrable, what is the meaning of other times? What is the geometric sense?
So here we have only one time, actually.
Yes.
But I'm a little bit confused because so here we did consider only one time. So we have 4 punctured sphere. Of course, we can consider n punctured sphere, and then we will obtain some more times and probably more complicated multi-particle systems.
But you use the traditional Liouville integrability or something else. If the first one, there is a family of commuting flows, the family of commuting Hamiltonians. The first one, the principal flow is related to the time, which is the position of the pole, and the dimension of the space is greater than in classical Painlevé equation. In classical,
okay.
So you have additional variables, additional dynamic variables, and I'd like to understand what is the meaning of additional times, additional flows on this phase space.
So I guess. So now we are talking about that when we have a multi-particle generalization, we have a little bit more spectral invariance. We have n spectral invariance.
Yeah.
And they, okay, since the situation is not...
Maybe I say one word and everything will be clear. When we extend the phase space for multi-particle, it is not extension. We don't extend number of times. We extend number of accessory parameters. It's this is another. That's what Ilya wanted to explain.
Okay.
Yeah, but generally we still have n commuting flows, but since we are talking about
always one time.
Yes, we have always one time, but this generalization will give me some more spectral invariance, so it will be a family of n Poisson commuting functions, but they depend on time. And this, so this is not a Arnold-Liouville integrability. In some sense, the Arnold-Liouville torus will change, how to say? So we may construct this map in some sense to the Arnold-Liouville torus, but it will change with the time. So when you change the time, the Arnold-Liouville torus will just change the, I don't know.
For example, for elliptic Calogero Painlevé, you should think about this time. It is not time, it is just a modulus of elliptic curve, and it is always one, because we have only one elliptic curve.
Mm-hmm.
In the Hamiltonian, we have it's two-dimensional system. In sense of if you write it like a connection, it's two-dimensional system with two parameters.
Okay. Ilya, you said something about quantization. What is the state of the art?
Sorry, I mean, what did I mean? The thing is that, let me just show you. So the things I said about the quantization are quite naive. So we have the Darboux coordinates. So we know how to quantize. Generally, we just send p P to D over D QI, and Q just goes to Q. And the thing is, when we have such Hamiltonians, where you have only polynomials in P, your quantization will give you, the quantization will give you differential operator. But for example, in Rusinar system, we have some rational function depends on the momentums, on P's in some sense. And when you will quantize them, you will have to consider the rational function of differential operator. And it will go to the difference operator probably. So it will be not just, it will be shift, not the derivative.
Yes, that's it. But have you some ideas of some geometric meaning of the quantization problem in this case?
You mean on the side of the isomonodromic problems, or
I mean,
what?
I mean the desired problem of quantum gravity.
No, I don't. I mean, I will just say no. Yeah, for a while.
Volodya, maybe you have some ideas about quantum gravity in this context.
Maybe we should ask Volodya.
How it relates to matrix models? Well, yes, but first of all, I think it's through what I ask you to think about with us about it. It's a kind of topological recursion should work. So we should go through topological recursion in this context. I think so. So it means that we should write analog of quantum spectral curves, because maybe we can use your spectral curves at least for rational case. This would be very interesting to write spectral curves for rational systems.
Volodya,
No, they are Hitchin systems, Dima. They are all Hitchin systems, but in Pickwick sense, in Pickwick sense, non-autonomous Hitchin systems in sense of Michal Aronovich and Levin.
Okay.
So they have spectral curves.
Yes, Volodya, but the time here, it is the modular parameter on the, so it's a parameter on modular space.
Forget about, let's consider just rational case. We have three interesting rational spectral curves, which should be quantized in sense, probably in sense of your quantization.
Okay.
And this is the first step, just, and then we will think about hyperbolic or elliptic, but we should start with three simple P1, P2, P4.
Absolutely.
What people in quantum field theory, people called Argyres-Douglas.
Yeah, moreover, I think maybe it's not the right reference, but maybe. So some of this, as far as I understand, this Hamiltonian system, which corresponds to P2, maybe. So there is a paper by Romanov who showed that if you will consider beta model, beta matrix model, and then we will write this So, well, you can consider some beta model, write some linear equation, and then the dynamic of the poles or zeros of this solution will be in the following form. I don't know if it's related to the question about the quantization, but it's how these systems related to the matrix model generally.
Yeah, and it is explicitly checked for the case of P2 in recent papers, Itz and Prokhorov.
Yeah, exactly. And
we are very happy that they used heavily our results, because Romanov did it before and he didn't know this. And he did it for a very special case. And Sashits and Prokhorov, they seriously extended it, but only for P2.
Okay, I hope we can continue this subject in 4 weeks. And now I'd like to thank all the participants and principally the speaker. Thank you, Ilya.
Thank you.
Good evening and bye.
Bye.
Right.